let me introduce the next speaker. Victor Erokhin was mentioned here before. Victor is the Director of Science at the Institute of Materials for Electronics and Magnetism part of the Italian National Council on Researchers. And Victor is the inventor of the Memristive device, I have to say, or memristor. I know that there's some...
No, Max told this, but it is not correct. In reality, it is not correct. The inventor is Leon Chua, and the first mentioning of device realization of this element was done in 2008 by Hewlett-Packard Group. What is correct, that I have done my device 3 years before Hewlett-Packard, but I didn't know the word memristor. So I begin to use this, and again, it is not memristor. Memristors doesn't exist. Everything must be called memristive devices. Okay. Today I won't say, this is very popular word, neuromorphic. But when people speak about neuromorphic, usually they understand different things under this word. Today in my short presentation, I would like to express my vision of neuromorphic systems. Probably it will be an expanded answer of the question you put yesterday to Max. Okay, from my point of view, the system, we can call it neuromorphic if it makes several functions. First of all, the system must use the same elements for memorizing and treatment of the information. And this is clear for everybody. Even in traditional electronics now, there is a concept of in-memory computing. But in traditional electronics, in-memory computing is done only for one reason. Because the slowest operation is a exchange of data between processor and memory. And doing in memory, it will be faster. Instead, in the brain, we use the same elements for memorizing and treatment of the information, but not for the speed. But learning is not only memorizing, but adaptation of the processor of the brain for solving similar tasks in the future. So, second thing, this system must allow parallel information processing. So, in single nucleus computing, each time only one operation is done. There are multi-nuclear computing where you can do several operations in the same time. It corresponds to the number of nuclei you have, but it is extremely energy consuming. For example, these video cards allow treatment of big data. They must be cooled. It should have used a system that cooling during the operation. Instead, in the brain, we do we have full amount of the information, visual, acoustical, tactile, and we treat it in the same time, simultaneously. Third thing, this system must allow internal activity, internal processes. I will speak later in more details about it. Next, it must allow biorealistic learning algorithms. Again, I will speak about it later. And very useful if the system allows 3D organization, as it is in the brain. And finally, it's also very good if it will allow coupling with living beings. Let us consider some points. This is a device I am working with. I don't go into the detail of its operation, but important. It is organic device, about inorganic device. It's a main road in Memristive devices. It will be 2 presentations in the afternoon, but I work with organics. What is important in this case, that the device has hysteresis in voltage current characteristic and rectification. Second important feature of this device, it is volatile device, and this is also important. It is necessary to have both volatile and not volatile devices if we want to make neuromorphic systems. First of all, as I told, we must have internal activity as we have in the brain. First of all, the device I have shown, a small modification of this device allow to transfer it into an auto-oscillation generation mode. And in this case, we have oscillating processes as we have in the living beings. Second thing, very important, the effect of noise. 10 years ago, there were only a couple of works where it has been demonstrated positive effect of noise in electronic devices. Because when we speak about traditional electronics, noise is always, practically always, not a good idea. People try to shield the devices, to fight against noises. However, during the last 5 years, it has been demonstrated, and it's a big advantage was done in Nizhny Novgorod, that noise play in living beings, it play a positive role, but also in neuromorphic devices, it play a positive role. Just to demonstrate, let us imagine that we have a system with several minima. And we want to classify events. Events in this case is these spheres that fall down on the system. If the system is not, if there is no noise, they form some distribution. Even some spheres can be outside minima. Instead, if we begin to apply noise, at a several level, all the spheres will be in minima, but not in a global minima. We increase noise, and we arrive to a situation when events were classified according to a global minima. If we will increase again the noise, it will come again to a random situation. Therefore, it exists an optimal level of noise when our system works better. And finally, as I told, during at least last 5 years, everybody begin to understand that noise is a positive event. Instead, the last thing, I will speak about the internal activity. Till now, not yet completely accepted by the society. It is crosstalk of elements. In traditional electronics, crosstalk of elements is absolutely negative phenomenon. Also in neuromorphic, according to the papers I read, usually people try to fight against crosstalk of elements. Instead, as we know, in our brain, there is crosstalk of elements. What does it mean? We think even when the external stimuli are absent. So our thinking is treatment of the already obtained information by crosstalk of neurons in our brain. And there are not so many experimental works on this. This is my work of some years ago, and this is a simple demonstration that crosstalk can play a positive role. This is only a circuit only of 2 elements, but what is important? That when we apply external stimuli, a chain of signal transfer is stable only when resistances of these elements are balanced. So, increase of the one resistance results that the potential is redistributed, and that with a high conductivity will be depressed, and with a low conductivity will be raised. And, for example, as far as I know, I am not a biologist, but epilepsy is a lack of inhibiting neurons. So, in this case, it will be done automatically. So, inhibition will be to stabilize the signal transfer chain. Okay, biorealistic learning algorithms. This is well-known STDP, spike timing dependent plasticity. And this is a mechanism that nature developed in order to establish automatically causal relationship. Let us imagine we have two neurons connected by synapse, and they are spiking. Let us call spike of the presynaptic neuron event 1, spike of the postsynaptic neuron event 2. So, if there is a big time difference between these spikes, nothing happens with synapse. But as shorter is the interval between these spikes, it means that synaptic weight is increasing. So, what does it mean? That event 1 is a reason for the appearance of the event 2. And as closer they are, as stronger is the synaptic connection. Vice versa, if postsynaptic spike is before presynaptic spike, if the time interval is long, nothing happened, but as shorter it is, as more suppressed is the synaptic connection. What does it mean? That event 1 cannot be a reason for the event 2. And from my point of view, this is really miracle. And in this case, with our devices, we have reproduced this kind of relationship. As you see, it is absolutely identical to a previous one, with the only difference that time scale is different. But these devices are rather macroscopic. Therefore, we can decrease this interval. And then such kind of behavior was used to reproduce Pavlov dog learning. As you remember, Pavlov dog experiment is giving food to a dog, making a bell ring, and after several repetitions, salivation become only just after the bell ring without the food. And in these cases, it has been done using one resistor in the chain of meat and one resistor and one memristor in the chain of sound. And a feedback of the output spike corresponding to salivation. And after several repetitions, we obtained that this quasi-dog begin to feel the presence of food just after the bell ring. I must say that there are many works where such kind of behavior have been reported, even with memristive devices. However, in this work, it was the first time where biorealistic spike timing dependent plasticity algorithm, learning algorithm, has been demonstrated using our memristive devices. Last thing, not last, it will be one more. Okay, here it was discussed and will be discussed realization of artificial neural networks, where it is demonstrated also that spiking systems are more effective. But okay, in spiking more effective, but comparing with traditional artificial neural networks, you need not single layer, but multi-layer. You need to know intermediate weights of connections of the layers after each epoch of learning. In this case, currently widely developed system is reservoir computing. What is this? You have a medium which can be considered like a black box. The only thing that within this medium system must have elements of this system must have short-term memory. And you apply input signals, and at the output, you need to have a traditional perceptron, for example, and to adjust a weight only of this output layer. And again, I will not go to the details, but we have organized a system where reservoir, strictly speaking, it is not reservoir, it is quasi-reservoir, was done on these memristive devices, volatile memristive devices I spoke about before, and the output layer was done on non-volatile memristor. And in this case, we were able to classify digits very effectively. Now it is, I'm practically finished. Okay, what is important here that in this case, we don't need to know state of intermediate layers. We need just to have a feedback between correct answer, correct classification, and a vector of input parameters. Now the step forward is, this is more reservoir because it's a stochastic organization of fibers having memristive properties. And last thing I speak today, probably it is a possibility of connecting live nervous cells through our devices. Here in this top view, it's a photograph of a slice of cortex of the rat, where we have connected two neurons with patch clamp electrodes. And first, we have studied that they are not naturally connected by synapses, by natural synapses. How we can check it? We excite one and see no activity on the other. Excite second and see no activity of the first. Then, when we connect them by our device, we saw that after passing spikes, the weight of synaptic connection, the resistance of memristive device, was decreased. And after a certain level, the second cell began to spike. And as stronger the synaptic connection became, as shorter was the time interval between pre- and postsynaptic spike. And we come to a value of about 2 milliseconds that correspond well to what we have in brain. Finally, this is the same. In the first slide, spiking was induced by external action. In this case, the cell was spiking automatically, say. It was not necessary to apply external excitation, and we see the same. After a certain level, spikes begin at the second device, and after they begin to spike, and time interval was about 2-3 milliseconds between pre- and postsynaptic spikes. And final thing I want to underline, probably Max will speak more about this, it is the energy efficiency. Why we need to do, say, all this conference mainly dedicated to software realization of bioplausible systems. However, and only we here are speaking about hardware. But why we speak about hardware? Because in brain, one event costs something about 10 femtojoule. My device is now about 10 picojoule per junction, but it is macroscopic device. So I hope that we will arrive at least to a level of 100 of femtojoule per junction. Instead, when we speak about software realization, one event is billion times more energy consuming than our devices. Thank you very much. The only last thing I want to say to you, to remind to you that now the submission for a special issue for bio-nanoscience dedicated to our session is open, and it will be closed 31 January. There, your contributions are welcome. Thank you very much.
Do we have any questions? Well, okay, you.
Why not? Yes, you know, we've been discussing. Could you give us some your ideas about the future of memristive technologies at high level? Just, yeah.
Look, probably Alexei will answer this question in the afternoon regarding inorganic systems, which is a main road of memristive technologies. Instead, dealing with organics, what we need to do? First, we need to decrease sizes of the devices. We need to establish technology of making chips. For example, the chip that Alexei bring to us today is based on CMOS technology, which is very well established. Instead, what I am doing, it was started from zero. The technology didn't exist. Therefore, we must bring it to a level that is comparable at least with CMOS technology.
Oh, no, that one.
Thank you very much. Yeah, thank you very much. It was interesting, very advanced lecture. My question, comparing to GPU devices, how is behaving your device, and on which data sets you trained, let's say, and evaluate your results?
Just to understand the question, first you want to know the working principle of the device, and second, what type of data we can classify. Okay.
Yes.
The working principle of the device is based on possibility of, in this particular case, of polyaniline to be in insulating or conducting state with intermediate states according to the redox condition of this polymer. When it is oxidized, it's conducting as a not good metal, as indium, for example. And when it is reduced, it is insulator, good insulator. And therefore, the working principle is such. You have a channel of polyaniline. In the middle part, there is a stripe of electrolyte. In this particular case, this is solid electrolyte based on polyethylene oxide doped with lithium salt. And you have a reference electrode that is connected to one of planar electrode of channel, and it is grounded. We apply potential to other electrode, and according to polarity and value of the applied potential, this zone, which is in contact with electrolyte, can be oxidized or reduced, because it is electrolyte. And therefore, you can change conductivity of the whole device. Both potentials, oxidizing and reduction potentials, are positive. Therefore, the device is volatile. So if you put 0, it is reduced automatically. So this is a working principle. What kind of data?
Because maybe the question, this was a very technical explanation. I think those who were at the workshop yesterday actually saw, Max showed actually the memristive device, how it functions.
No. He showed absolutely different device with a filament formation.
Right, but
it is different.
Right, but I think maybe the question here, the GPU, maybe I understood correctly. I think that what
maybe more high level comparing
on a high level,
yeah.
the architecture changes just like our brain as information flows through it, while the GPU is static, like on a very basic level. Maybe that was the.
And the second your question was not very technical. So what kind of data we can classify? The first, when we about 8 years ago, we have realized single layer and double layer perceptron, and it was done for classification of signals according to a logical function. In the case of a single layer perceptron, it was done not AND and not OR classification, but with a double layer, it was done exclusive AND. Because it cannot be classified with a single layer perceptron, because in this case, in the case of XOR, you have 2 diagonal ones and 2 diagonal 0, and doesn't exist a line of a first order that can separate these 2 classes. Therefore, you, by definition, need to have a double layer perceptron. It has been done and classified. And as I showed in my some last slides, reservoir computing has been done for classifying digits. And now it is in press. These data were experimental. But now we have submitted a paper where it is demonstrated, but theoretically, that this system can be useful also for recognition of handwritten digits. Therefore, this is one thing. The second thing can be a speech recognition. Now we are speaking about Max, about Irina, to try to use it for translation of emotional color of speech.
I thought maybe that you had some EEG data from the brain.
Yes,
directly,
yes.
And convert to digits. Okay.
Yes. Now we are working on this. I have nothing to demonstrate, but we use not directly EEG data, but we use a data set available in instruments, in internet, trying to classify this mental activity.
Oh, great. Thank you.
Thank you.
Any other questions?
Just a comment while the microphone is in my hands. This was a wonderful lecture, and while listening, I saw great potential for generalizations in theoretical means and all these things you said. There were citations to several articles in different disciplines, so huge potential. Yeah. When you said noise, crosstalk, I thought about mutation, evolutionary computing. When you said global minimum maxima, so many things, it is interconnected. Yeah.
Absolutely agree with you. I just listed the things I was thinking about, and there are much more to be considered.
Yes,
Thank
crosstalk, maybe that's empathy in Irina's work and something like that. Yes, that's all. Thank you.
Anybody else? All right. Yes.
So in your memristive device implementation, do you have any notion of cellular diversity, or all neuron or neural-like units, are they identical?
Okay. This is a good question. As I told, answering the question of Max, we don't have a technology. Therefore, with respect to devices that Alexei is doing, in our case, device-to-device variety is much more with respect to devices, inorganic devices, done based on CMOS technology. However, when I spoke about crosstalk, if you speak about not one device, but an array of devices, they will automatically adjust their values in such a way that the system, the whole system, will not. In any case, it will be different because we are done from our brains are done from neurons, but all of us are different. We have some features similar, but we have a variation.
All right. If that's it,
Thank you very much.
thank you all.